Yes, so today we are going to discuss the Diophantine equation. Actually, the Diophantine equation is a equation, can be any equation, which is to be solved in integers. Thing is that, okay? And the simplest form of this equation is ax plus by equals to c. This is the simplest form, okay? Uh, the Diophantine equation is named after the mathematician or philosopher, what we can say, that Diophantine, and he lived around 250 AD in Alexandria. In fact, nothing much is known about his life and all, but some concrete uh, evidence can be obtained from the book by Bishop. He was his friend, the friend of Diophantine, and he dedicated his one of his book on Egyptian computation to his friend Diophantine. And there is something which we can find from a kind of equation about the age of Diophantine of Diophantine, but thing is that we don't know exact date of birth and when he died. So there is a question kind of thing or formulation kind of thing, which is in this paragraph. What personal particular we have of his career come about the wordings of epigram problem, apparently dating from 4th century to the effect. So in this it is written that his boyhood lasted 1/6 of his life. His beard grew after 1/12 more. And after 1/7 more he married. And his son was born 5 years later. 5 years later. The son lived to half his father's age, and the father died 4 years after his son. If X was the age at which the Diophantine died, and these data lead to the equation. So this is the equation based on the above data, starting from that his boyhood lasted in 1/6 of his life. So it contributes. If X was his life or age, then we can write it down X by 6. And then his beard grew in after 1/12 more. Then we can write X over 12. So similarly, we can write plus X by 7 plus 5 plus X by 2 plus 4. And this should altogether makes the age of Diophantine. So when we solve this, we come to know that the solution of this equation comes out to be 84. So this is the thing what we know, that he lived around 84 years. Thing is that, but he contributed so many things in integers or in solving the equations, solving the equation in the set of integers. Okay. So let us see what is the general form and all. We can write Diophantine equation. Okay. In fact, the term, this term, the Diophantine equation, the term Diophantine equation, the Diophantine equation is applied. You can apply it anywhere where you are searching for integer solutions. Okay, applied to any equation in one or more unknowns which to be solved in the integers. Okay, and the simplest form we can consider, the simplest form, the simplest form, uh, the simplest form or the simplest type you can write. Okay, the simplest type of the Diophantine equation. Diophantine equation is ax plus by equals to c, where a, b, and c belongs to the set of integers, and a, b, a, b not 0, both not 0 or not 0 together. Okay. Okay. Or we can write both not 0. Fine. So actually, when we or we can write because we are looking for the solution of this. So and greatest common divisor will play a role. So if you take some any 0 and then some non-zero, then it may be problem. Anyway, A, B uh, not both 0. You can write like this, or you can write uh, that not 0 together. Okay. So suppose this is a equation number 1. If a solution of a solution of one, a solution of one is a pair of integers x0 y0, such that as you know that ax naught plus by naught equals to c. Okay, so you know that this kind of equation, I think this kind of equation may or may not have a solution. Okay, in fact, if you're talking about integer solution, okay, this kind of equation in general, if you are solving that in this equation in the set of real numbers, then we are going to certainly have so many solutions for this equation. But thing is that if you are looking for integral solution or integer solution, then it may or may not have. For example, for example, consider what we can consider. We can consider the equation 3x plus 6y equals to 18. This equation need to be solved in integers. Okay. Of course, this equation will have so many solutions in set of real number, but we are interested in integer solution. It means that when we are looking for integer solution, then we can say that this is a Diophantine equation. That's all. If you're not looking for the integer solution in particular, then we cannot say. Okay, so Diophantine equation is a given name to the equation for which we are looking for integer solutions. Okay, so this equation has several solutions, such as what solution we can get 4 1. There is one solution to it, and then minus 6 6 another solution. 10 negative 2 is another solution to this equation. You can see that 3 times 4 plus 6 times 1 for this. Okay, So in left hand side, we have 4 times 3, that is 12 plus 6 equals to 18. So this is a solution. Okay, and then we have another minus 6, 3 times negative 6. Okay, and then 6 times 6. So this makes my negative 36, and this is just a minute. I think I negative 36, or I think I did some mistake or what. No, 18. This is 18 and this is 36. So this is going to be 18. Okay. And then 3 times 10 we can write, and then 6 times negative 2. So 30 minus 12, that is equals to 18. Okay. So these are the solutions to this equation. Okay. But if we see if you see some other equation, then we may have some equation where we don't have any solution. Okay. On the other hand, consider another example. We can consider another example for let us 2x plus 10y equals to, maybe we can write 19. All right. So do you have any idea about the solution of this equation in integers? This equation has any solution in integers? I'm just asking you.
No, sir. Will not have any solution.
Why?
The left hand side will always be even.
Very good. Okay. You can note down 1 point for this. Yes, left hand side is always even irrespective of value of x and y. And remember that we are looking for x, y in integers. Of course, if x, y we are not taking integer, then we can get some real number, so that it will have some solution. In fact, many solutions. Okay. So this equation has no solution in integers. Fine. So what we can say, in any equation of this form, thus an equation of the form ax plus by equals to c may or may not have any solution. Okay. So natural question is that under what condition this equation will have a solution. Okay. So this is a natural question. So next result, we are going to see under what condition this kind of equation will have a solution, or the Diophantine equation has a solution. Okay. So this is a solvability condition. Solvability condition. The Diophantine equation ax plus by equals to c has a solution, or admits a solution if and only if d divides c, where d equals to the greatest common divisor of a and b. Okay. Of course, there is a Another result we will be seeing how we can find other solutions if one solution is known. Okay. Just like in the first example today we have discussed, in that we could find three solutions to a given linear Diophantine equation. Okay. So if one solution is known, how we can derive or how we can get another solution, or we need to find separately them separately. Okay. So that we'll see. And this condition is nothing but this is a necessary and sufficient condition for a equation, for a linear Diophantine equation to have a solution. Okay. So let us see the proof of this. Since D equals to the greatest common divisor of A and B, this is the greatest common divisor. So there exist R and S, they are integers such that this is the greatest common divisor. So D divides A and D divides B such that A equals to D times R and B equals to D times S, like this. Okay. Now, because this is if and only if condition, so let us assume that AX plus BY equals to C has a solution. Okay. So suppose AX plus BY equals to C has a solution, and let us say X naught and Y naught. This is a solution. Okay. So this implies that C equals to AX naught plus B Y naught. All right. And A is nothing but a dr. So we can write here dr X naught plus ds X naught. So this is equals to D times R X naught plus S times Y naught. So what we have? We have a C equals to D times or X naught S Y naught, and R and X naught S and Y naught, they are integers, so their product and sum will is also going to be an integer. So this would imply that D divides C. So we have one part. We proved one part. The second part, the converse part, let us assume conversely, let D divide C, where D is the greatest common divisor of A and B. Okay. So since D divides C, D divides C, so there exists some integer T such that C equals to D times T. Okay. Okay. Also, you must be knowing that if D is a because D is the greatest common divisor, so it can be written as A X naught plus B Y naught, something like this. Okay. Also, since D is the greatest common divisor of A and B, so there exists X naught Y naught. This is different from this solution. Okay, but this is X naught and Y naught. They are integers such that D equals to A X naught plus B Y naught. Do you know this result?
Yes, sir.
You must have read it before, if you can recall. छोटी classes में है ना? So this we have. So this implies that let us multiply both sides by t. So we have a dt in the left hand side. In the right hand side, we can write a and then x naught t plus b and y naught t like this. Okay. D times t is nothing but c. So in the left hand side, we have c. So this implies that c equals to a x naught t plus b y naught t. Okay. So this implies that x dash equals to x naught t and y dash equals to y naught t. Is a solution of ax plus by equals to c. So this is solution of this equation. Okay. So this result gives us the condition under which a linear Diophantine equation has a or admits a solution. So in this case, in this equation, if you see the greatest common divisor of 2 and 10 is what? Hello?
2.
Yeah. And 2 doesn't divide? It's 10, 19. So
19.
that's why there is no solution. And in this case, you see the greatest common divisor of 3 and 6 is the 6. It's 3, and 3 divides 18. So that's why there are solutions. Wait, okay. Letter. Now thing is that if you see here, the greatest common divisor 3 of 3 and 6 is 3. Okay. So somehow we will retain here 3 solutions to it. Okay. Greatest common divisor of 3 and 6 is 3, and 3 divides 18, and therefore it has a solution based on the result we have just discussed. Okay. And somehow we are able to see that there are 3 solutions. Okay. You can search it out for more if you can find. Okay. But one thing we can relate that because greatest common divisor of 3 and 6 is 3, and that is value of d is 3. So we have 3 solutions here. Okay. In case if suppose if the coefficient of x and y, that is they are a and b, if they are relatively prime, then their greatest common divisor would be what? 1. Huh? So we may expect that there should be unique solution to it, but that we'll see later. Huh? Now next there is another result, more general result. This theorem says that the linear Diophantine equation ax plus by equals to c has a solution if and only if d divides c, where d is the greatest common divisor of a and b. So this part we have done. Next part is that if x naught and y naught is any particular solution of this equation, then all other solutions are given by the expressions below. Okay, for varying integers t. So this result not only guarantees or gives the necessary and sufficient condition for a Diophantine equation to have a solution, but it also gives formula with the help of which we can find all solutions if it exists. Okay, so अगर एक solution मिल गया तो उसकी हेल्प से और भी solutions हम find कर सकते हैं. Okay, fine. So let us see how we can let us try to prove this. So first part we have done, huh? First part we have done already. Okay, so let us try to prove the second part. Okay, for second part, For second part, assume that x naught y naught be a known solution. The second part says that if some solution is known, then we can find other solutions also. Known solution of ax plus by equals to c. Okay. If x prime and y prime is any other solution of this equation, then how we can write a x naught plus b y naught, this is equals to c, and this is equals to a x prime plus b y prime. Okay, so this implies that a x naught and then x dash, and this is equals to b, and then b y naught and y dash. So this implies that okay. Now since suppose this is number 2. Okay, since D is the greatest common divisor of A and B, so there exist integers R and S such that greatest common divisor of RS equals to 1, and since D is the greatest common divisor of A and B, so D divides A and D divides B also. So A equals to dr and B equals to ds, like this. Okay, so from 1, we can write in left hand side we can substitute this, and in the right hand side this. Okay, so we have dr x naught minus x dash, and in the right hand side we have ds and y naught minus y dash. So d gets cancelled. So we have r x naught minus x dash and s y naught minus y dash. Okay. So this implies that r divides y minus y dash, y naught minus y dash, as r and s are relatively prime. Okay. In fact, this is from there is a result that if some number, suppose for example a divides b and c, and a and c are relatively prime, then certainly a is going to divide b. Fine. So this kind of this is called sometimes Euclid lemma. Okay. Okay. So r divides y naught minus y dash. So this implies that y naught minus y dash, this is equals to some, just a minute, I think okay, r times t. Okay, for some integer t. Okay, all right. So we have y naught minus y dash equals to rt. So from equation number 2, substitute the value or the equivalent expression for y naught minus y dash in the right hand side. We have a x naught x dash, this is equals to b rt. Just a minute. If okay, equals to R times okay. No. We can substitute here. Okay, we can substitute it here. So from here we get R x naught minus x dash. This is equals to s times y minus y dash. The value of this is R times t. So R and R gets cancelled from both sides. So x naught minus x dash, this is equals to R times t. Okay. No, s times t. This is s times t. So this gives us x dash equals to x naught plus st. Okay. Because x naught is known and st also known. So s is also known. So we can find it out. The solutions, other solutions. Okay, so from here we can have x dash equals to x naught. This is a fixed because this is a known solution, and then s is nothing but b by d times t. And similarly, we can find out y equals to y naught minus rt, and this is equals to y naught minus a by d times t. Okay. Fine. So this is going to be solution of the Diophantine equation. So once we know x naught y naught, one solution of the Diophantine equation, and of course d is going to be the greatest common divisor of a and b. So d is also known. A and b are also known. So d is any integer. Okay. So corresponding to each integer, we have a solution. Okay. So we will see what are the
Actually, sir.
possibilities. Yeah.
जी सर x डैश इक्वल टू x नॉट माइनस होगा सर यहाँ पे b by d.
X dash equals to
x डैश इक्वल टू x नॉट माइनस st.
Okay. Yes. Yes, we will take this to this side, and this will give us x naught minus st. X naught minus st. Yeah? Here minus.
Yes sir.
Okay. Thank you. X naught minus st. Okay. Thank you. So here, I think here we can change them. Here minus, and then here there should be plus, I think. Huh? We can from here we can see y naught minus y prime equals to this one. So this is going to be y prime equals to y naught minus rt, something like this, I think. Huh? Yes.
सर शुरुआत में ही सर गलती हुई है सर. ax नॉट प्लस by नॉट इक्वल टू ax डैश प्लस by डैश. सर इक्वेशन 1 है सर. इसमें यहाँ पे सर y डैश माइनस y नॉट होगा. by डैश माइनस y नॉट.
Yes. Here somewhere. Huh?
Yes sir.
Okay. Yeah, either I can write here dash or here is prime. Yeah, here
Yes
we
sir.
have done thing. Okay. So I think let me change this one so that it could be in uniform with your book. Okay. So here we can write x dash and x naught. So here we can change more. Here. Okay. So here we can write x dash minus x naught. X dash minus x naught. I think rest is okay. Here also. Okay. here x dash, x naught, x dash and x naught. So x dash equals to x naught plus st. I think it is okay now.
Yes, sir.
Okay. And then here we should have plus and here minus. Okay, thank you. Thank you. I think Saurav.
Yes, sir.
Thank you. Good. Otherwise बाद में problem करता है. ठीक है. Thank you so much. So here I think it is okay now. So this is a solution. And a verification you can do. For verification you can a x dash plus b y dash. This is equals to, you can write the value of x dash here. So x naught plus b by d times t plus b, and then y naught minus a by d times t. This is equals to a x naught plus b y naught plus, and then from here t we can take common, and ab we can take I think, yeah, abt, ab by d minus ab by d, and then t is there. So this becomes 0, and this is ax plus by plus 0, and x naught y naught. This is a solution of the Diophantine equation. So this is going to be C. Huh? So what we have? We have a x dash plus b y dash equals to C. So this is this proves that if one solution is known, then for corresponding to each t, we can have a solution to the linear Diophantine equation. Okay. All right.
Yes, sir.
Now we can try. You can try to solve this example. Solve the Diophantine equation. The Diophantine equation. 172x plus 20y equals to 10,000. Okay. Of course, you can make them these coefficients small by dividing some number maybe. Okay. And then you can try to solve it. The solution of this is there. Let me show you. This is a question from your book. So this is a equation, and 172 and 20. The greatest common divisor of this is they are applying Euclid algorithm to find the greatest common divisor. Okay. So for greatest common divisor, they are just using this algorithm. So when 72, they are dividing by. You need to find out the largest among them. Okay, larger among them. So 172 and 20. So 172 is bigger than 20. So divide it 172 by 20, and then it 8 times 160, and then plus 12. This is a remainder. Okay, and then again divide this by the remainder. So you are going to get another remainder. Then 12 is there, divided 12 by 8. So you are going to get another remainder 4. And then you have 8 here. Okay. So you divide with it with remainder, and then you are going to get 8 equals to 4 times 2. So the last non-zero remainder is the greatest common divisor. So remainders were 12, 8, and 4. So last non-zero remainder is 4. So greatest common divisor is going to be 4. This we have done in early classes. And since 4 divides 1000, so therefore it has so many solutions. Their solution exists. Okay. What solutions? So at least we need to know one solution. The above result, this result says that if one solution is known, x naught, y naught, This is any particular solution, there are other solutions we can find it out, okay, using this formula. So let us see. So to find out solution of this equation, we start from here. Okay, we start from here. From here. So we can write 4 as 12 minus 1 times 8. So 8 you can write from here, 20 minus 12, and then you will be getting 20. So you please don't write like this 24. Okay, you have to write 2 times 12 and minus 20. And then 2 times 12 minus 20, and 20 you can write from here, 20 you can write from here. So 12 plus 8, sorry, here, okay, 172, something like this, okay. So 172, this 12 you have to write this 12, you have to write 172 minus 8 times 20. Minus 8 times 20 minus 20, and then 2 times 172, and then 2 times 8 times 20. Okay, so 2 times 8, that is 16, and 1 time negative 20 is here, so minus 1720. Okay, so 172 times x 1 and 20 times this y is equals to 4. So what is the solution? X equals to 2 and y equals to negative 17. All right. So this is a solution we are having for this equation. And then once we know this solution, then other solution we can find it out using this formula. Okay, fine. And if moreover we are interested in positive solutions, then we need to put condition. This should be greater than 0, and this should also be greater than 0.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.